In this section, we are going to learn about similar matrices. And to kind of motivate the definition of similar matrices, I want to actually start with an example from calculus. Now, this example doesn't really directly relate to the idea of similar matrices, but we will kind of be able to see the same kind of mathematical phenomenon here that we will see with similar matrices. All right. So how do we integrate this? This is an indefinite integral. The integrand is 2x sine x squared plus 1. So this is a pretty straightforward substitution problem. So I'm going to select u equal x squared plus 1. The derivative of u with respect to x is 2x. And so du is equal to 2x dx. I could swap out 2x and dx together for du. And so the indefinite integral becomes, after I do the substitution, sine of x squared of 1, sine of x squared plus 1 becomes sine of u. And 2x dx, 2x times dx is my du. Okay? So notice we have changed the problem, and in so doing, we have a much easier problem to work with now, right? The antiderivative of sine of u is negative cosine of u plus a constant. And then in the final step, our starting variable was x, so we want our ending variable to also be x. So I'm going to swap out u with x squared plus 1 again. So negative cosine of x squared plus 1 plus c. All right? So I just want to draw your attention to what we did here. Our very first step, we performed substitution. Let me see if I can fit that on the line. Substitution. Okay? Why? Well, this looked like a hard problem all by itself, right? We didn't know the antiderivative of 2x sine x squared plus 1 right off the top of our head. But by doing substitution, we were able to convert this harder problem to a similar, easier problem. Okay, the two problems are related, but this is much easier to work with, right? So once we got it here, we were able to take the antiderivative, but then this isn't the actual answer we wanted, right? So we need to substitute it back. This was the easier, this was a solution to the easier version of the problem. We needed to substitute back to see how that related to our original problem. Okay, so keep this in mind as we now define similar matrices. So if A and B are two n by n matrices, we say that A and B are similar if B is equal to P inverse times A times P for some invertible matrix P. Okay? If the two matrices are similar, we use the tilde symbol and we say A is similar to B. Okay. So kind of an interesting definition. How does it relate to what we just did with integration? Well, notice the idea here is we did something, we substituted to get to an easier problem. We were able to work with the easier problem, and then we were able to substitute back. All right? This is something we do pretty often in mathematics. We see if we can relate it to some easier problem in some way that we can change into that easier problem and then change back. We're doing the same thing here, okay? So maybe matrix A is easier to work with than matrix B. So what we could do is we could first change into a new paradigm where we're working with matrix A. So matrix P kind of is like the substitution step in the example above. Okay, changes things into an easier problem. Then we solve the easier problem, and then we need to relate it back to our original problem, so we change back. Okay, we substitute back. With matrices, it's exactly the same. We apply matrix P so that we can work with the easier matrix A, and then we go back to P inverse. P inverse lets us go back to the original problem. Okay? Now, I should emphasize matrix A doesn't have to be easier to work with than matrix B, but this might be an example of where this might be a useful situation to work with similar matrices. Okay? Kind of like how using substitution, we don't have to always get an easier integral when we perform substitution, right? It's possible, theoretically, to do a substitution and get a harder integral to work with. Doesn't mean the math's wrong, but it does mean that it may not be especially useful. Same thing here, okay? Applying matrix P doesn't necessarily mean we'll get an easier matrix A to work with, but maybe we would. Okay, if we can choose P in such a way so that A is easier to work with, then that might be easier to do than just to work with B directly. All right, I hope that makes sense. So there are a lot of similarities. There are a lot of properties that two similar matrices have in common. Okay, let me just keep the definition in there for now. Similarity is an equivalence relation. An equivalence relation, we haven't defined it before, but it is a relationship that is similar to equality. It has some features that are like equality, but it's not necessarily equality in the way we usually think of it. All right, but it has three properties. Reflexivity, that is, any matrix is similar with itself. Just like if I have a number, it is equal to itself. Right? Symmetry. If A is similar to B, then B is similar to A. Just like if 3 equals 2, then also 2 equals 3. And transitivity. That is, if A is similar to B and B is similar to C, then A is also similar to C. Just like if X equals Y and Y equals Z, then we know that that means that X must be equal to Z also, right? Okay, so as I said, it's not equality, but it has these three properties just like equality does. So we call it an equivalence relation. They have a kind of, the relationship is kind of like equality. It forms a kind of an equivalence. Okay? Okay. So we actually need to prove this. Prove that matrix similarity is an equivalence relationship. So for part A, observe A is equal to I inverse AI. So A is similar to A. So just remember what our definition of similarity is. Okay? A is similar to B if B can be written in the form of the inverse of some matrix times A times the original matrix. Okay? Doesn't matter what these two matrices are as long as it's invertible. So that's what I did here. I said A is equal to the inverse of some matrix times A times the original matrix. Okay? That means that A is similar to A, if I can write it in this form. Okay? Now part B. If A is similar to B, then B is similar to A. So since A is similar to B, what was the definition again? If A is similar to B, then I can write B as P inverse AP for some invertible matrix P. Okay, so let's use that definition. Since A is similar to B, there exists an invertible matrix P so that B equals P inverse AP. Okay, so I haven't proven anything yet. I'm just using the assumption. For part B, the assumption is A is similar to B. What I need to show is that B is similar to A. So this means that A needs to be equal to the inverse of some matrix. I've already used P down here, so I don't know, maybe Q. Q inverse B, Q. If I can show that that's also true for some matrix Q, then I'm done. Okay? So what I'm going to do is I'm going to start by moving P inverse and P to the other side. Left multiply. Both sides of the equation by P, and right multiply both sides by P inverse to obtain. So remember, matrix multiplication isn't commutative, so we have to be very careful that where if we multiply something on the left on one side of the equation, we have to multiply on the left on the other side of the equation also. It has to be on the same side of each side of the equation. Let me show you. It'll make a little more sense. Okay? So I'm going to left multiply both sides of the equation by P. So I've got the equation. Too much room there. So I'm going to left multiply both sides by P. So on the left of both sides of the equation, I'm going to multiply by P. Okay? So I've left multiplied by P, which means I've multiplied P on the left side of both expressions on each side of the equation. And I'm going to right multiply both sides by P inverse. So multiply P inverse on the right on both sides of the equation. Okay? Now what does that do? Well, P times P inverse, those cancel, I just get the identity. P times P inverse, those cancel, I just get the identity. So on the right-hand side, identity A, identity is just matrix A. And on the left-hand side, I have P, B, P inverse. Okay? And this is almost what I want. The definition is the inverse should go first, then the original after. But matrix P is just the inverse of the inverse, right? So if P inverse is now what I'm thinking of as the original matrix, then I have the inverse of this times matrix B times P inverse equals matrix A. And that's the form that I have here in the definition. This matrix is similar to this matrix if I have the inverse on the left, the original on the right. So the inverse of this on the left, and then the original on the right. So let's see, that was A is similar to B, so B is similar to A. Okay? So from this point on, if I say A is similar to B or B is similar to A, you could think of it as being the same thing. All right? So that means A is equal to P inverse BP, but also B is equal to some other matrix, let's call it Q, Q inverse A, Q. All right? Both are true. If either one of these are true, then both of these are true. Okay, so that proves part B. Now part C, transitivity. So I know that A is similar to B, and I know B is similar to C. Let A be similar to B, and B be similar to C. So now we're going to use the definition of similarity. Then there exist invertible matrices P and Q so if A is similar to B, that means B is equal to P inverse AP for some matrix P. Actually, let me move that left a little bit. And B is similar to C, so that means C is equal to Q inverse BQ for some matrix B. Okay, just using the definition of similar matrices. Right? Now, what I want to show is that A is similar to C. So let's see, I've used PQ, let's use letter R. That means I want to show C is equal to some matrix R times R inverse AR. Okay, that's my goal. So how could I combine these to reach that goal? Well, I know B is equal to P inverse AP. I know C is equal to Q inverse BQ. So let's combine them to relate A and C together and kind of cut out the middleman B. Then substituting the first equation into the second. We have, so I'm going to, B is equal to P inverse AP, so I'm going to swap out B with P inverse AP. So I get C equals Q inverse, and then instead of B, I have P inverse AP, and then Q on the other side. So that's Q inverse P inverse, just kind of grouping things differently, times PQ. And remember, the product of inverses is not quite the inverse of the products. We have to flip it around. Q inverse P inverse is the same as P times Q inverse. Okay, remember the sock shoes property. You put on socks and then put on shoes. To take them off, you have to first take off your shoes and then take off your socks. Okay, so notice we've actually gotten to where we want to go. To say C is similar to A, then that means C is equal to the inverse of some matrix times A times the matrix. So if PQ is our matrix, if C equals the inverse of PQ times A times PQ, that's the definition of similarity. So meaning A and C are similar matrices.